In this video, it looks like we're going to cover the moment of inertia. It's one of the more difficult concepts to understand. It's just because it takes a little bit of getting used to. One thing we're doing with rotation and angular things is mixing in with multiple units. So right now we're in kinematics. We'll go ahead and throw in a couple things here. We'll mix in some things along the way with momentum and other units as we go, and just kind of throw the rotational part of momentum, the rotational part or angular part of kinematics in there to kind of not necessarily have a rotational unit, but see how it relates to everything we do. So reviewing the concepts of linear, where we have position, linear motion where we have position is x, velocity is v, and acceleration is a, and that when it comes to rotation or angular things, we deal with rotation as like an angle. Sweeping through that angle is our position, and angular velocity and angular acceleration, and how we can go back and forth between those two different quantities is using these equations where x equals r theta, velocity equals r omega, and acceleration equals r alpha, where we can transition between linear and rotational values very seamlessly. The other one that we need to talk about is inertia. And inertia that you learned in AP Physics 1 is the object's ability to resist changes in motion. And it's a property of matter, and so we usually tend to refer to that as mass. And so when physics, when something is resisting the change in motion, it has more mass and therefore more inertia. So it resists the change of motion or keep doing whatever it's doing. An object in motion will stay in motion, or an object at rest will stay at rest. That is a measure of its inertia. The more mass it has, the more it will stay in motion, or the more it will stay at rest. And so mass is that quantity represented by m, and we define that as the resistance to change in motion. The rotational or angular part of that we call the moment of inertia, and it's represented by I. And it's resist to change and rotation. Or spinning. It's probably the better way of doing it. And so we're looking at angular motion, and if things are going to spin, it has a moment of inertia we represent with I. For inertia, we represent the equation for that for F equals ma in Newton's second law, where the force equals the mass times the acceleration of that object. And with moment of inertia, we have Newton's second law, where its torque equals the moment of inertia times alpha. And it behaves just like mass. And so that's the important part of what a moment of inertia is. So basically, just like with Newton's second law, the more mass I have, the harder it is to accelerate that object. With moment of inertia, the more I, or moment of inertia, that I have, the harder it is to get that angular velocity to increase, to change the angular velocity and get the object to spin. Or if it's spinning, it's harder to get it to stop, and that the torque that is required to do that depends on that moment of inertia and how you can make that change. Alright, so the simple definition for moment of inertia for any single object that is rotating some radius away from a center is that it is the mass multiplied by that radius it is away from that center squared. So here I'm drawing a mass, a radius r away from a pivot point, and in order to accelerate or to make that mass spin, okay, I have to fight mr squared. I have to fight basically its moment of inertia, that mr squared. I have to fight it. I have to overcome it. And an easy way to think about it is if we were to double the radius it was away from its object, it causes double the radius the mass is away from its pivot point, it causes the moment of inertia to increase by a rate of 4 because that radius is now squared. This case is considered one of our simplest cases, and we call this the moment for a point mass. The next one we're going to deal with is a ring. And a ring is a lot like a point mass. That mass is rotating around the outer edge, and it just is spinning about that outer edge. And so at some radius away from the center, the moment of inertia for a ring is still mr squared. It's much like a point mass. It's just spread out all along the edge of the object. The next one we're going to talk about is a disk. Now a disk, it's basically the same mass as our ring above and has the same radius, but all that mass is more evenly distributed where it's closer to the center, and so its moment of inertia is a little bit easier to deal with. It's easier to rotate a disk that has the same mass as our ring above, where all that mass is on the edge in that ring. Now it's kind of more evenly distributed with some of the mass closer to the center. It makes the object easier to rotate, has less inertia or moment of inertia to cause it to help it spin. Like you can get it to spin easier. You can see this with bike riders. You can see how sometimes they have that solid wheel on the back. It's easier to rotate that solid wheel, and therefore since it's easier to do, it doesn't resist the change in motion as much. You get more of an angular velocity out of that. The next one we're going to deal with is a little bit harder to draw. It's a solid sphere, so you're going to have to bear with me as I try to draw this. But this is supposed to be a solid sphere. And this sphere, with all the mass, the same amount of mass as the ring and the disk drawn above, but it's, again, more evenly distributed. It doesn't take as much moment of inertia. It doesn't take as much effort, let's just call it effort, to get this thing to spin. And so because it doesn't resist the change in motion as much, it's more centered. And then in these things you have to notice are things that we tried to memorize last year in AP1, and they provided them for you on the exam. Like when they asked you these questions, they provided the equations for you in the question. This is one of those things you're probably going to have to memorize for APC. Because if you go start searching for these equations on the formula chart, and these are going to be multiple choice questions that come up, it's easier to just have this memorized and know these by heart. It's something that's very important for you to have ingrained in your memory so you can kind of fly through these questions. It'll allow you to kind of get through these a little bit quicker and not have to shuffle around looking for the equation. We have two more, and the first one is going to be a rod that's going to pivot about its center of mass. So the moment of inertia of the rod that's pivoting about its center of mass is 1/12 ml squared, where m is the mass of the rod and L is the length of the rod. The other one is the exact same rod, where we're going to pivot about the end of it, and it becomes 1/3 ml squared. So both these are the same rod, they have the exact same mass, they have the length of the rod is the exact same. So the ml is going to be similar between the two of them. It's just the fraction in front of them. It causes the moment of inertia to be different based on where you're pivoting it on the object. You can try this at your house. If you have a baseball bat, you can try to grab it near its center of mass. It won't necessarily be in the center of the baseball bat, more toward the barrel most likely, but it's easier to grab the object that it's a baseball bat if it's center of mass and rotate it rather than grab it by its end. It becomes a little bit more sluggish to rotate it about its end. If you don't have a baseball bat laying around the house, hopefully you have, well, heck, maybe you have a meter stick. I don't know. But whatever you have at your house, you could take this and try to rotate it and try to see if you can't see the difference between the two. Now there's a relationship between these two particular moments of inertia that we're talking about. That is the next thing that we're going to discuss, and it's called the parallel axis theorem. And so we're going to include both of these and create a relationship. And this is not an easy thing to go through, but hopefully we can make sense of it here. So what we're going to do to try to make sense of this is we're going to take the rod where it has a known center of mass and has a known moment of inertia of 1/12 ml squared, and rotate it about a different point on the rod, which will be the end, to try to make some good sense of this. So we're going to label two lengths here. The first length being the length of the whole rod, we'll call it L, and the other length being the length from the center of mass, we'll call L over 2, because it's right in the center in this case. Parallel axis theorem will teach us two things when we try to spin it about this point here on the end. The first thing we're going to see is that object, this rod, rotate about its center of mass. It'll rotate about that point, which is going to be 1/12 ml squared. The second thing we're going to see is we're going to see it rotate about that point mass on the end. Much like a point mass. To visually see this example while you're sitting here taking notes, grab your pencil or pen by the eraser end or the clicker end and rotate the pen from one side to the other just by rotating your wrist, and you can see that the object itself is rotating about a pivot point like a point mass, but if you look at the center of mass, it also is rotating back and forth. So we have to deal with the moment of inertia of both points, and therefore our moment of inertia has to account for both things. We see both of those things in that rotation. So as we take and do this math, we just rewrite what we have above there, and then we distribute the square into that. Back this up a little bit. Distribute the square. So we square the L and then we square the 2 on the point mass, and we end up with 1/12 ml squared plus ml squared over 4. Then what we try to do is try to get a common denominator here. And so we're going to go ahead and get a common denominator, which we have 3L squared over 12. And add those together and we get 4/12 ml squared, which is basically equal to 1/3 ml squared. I need to back this up a little bit. The parallel axis theorem works whenever we're spinning an object or rotating an object that is not rotating about its center of mass. So the common thing we're going to get is this equation here. This equation is written that I, about some pivot point that we'll call h away, and h being a distance away, is equal to the moment of inertia about the center of mass plus the point mass that is h away from that center of mass squared. In our example here, we had where this distance L over 2 equaled h, because we were h distance away from the center of mass. So we were rotating like a point mass around that red axis there, with that point mass rotating about that red axis where we were holding on the end of our pencil or the clicker point of our pen earlier. So we are expecting to get something like 1/3 ml squared when we do the parallel axis theorem. And this is our typical equation where we have I, or the moment of inertia that is h away, a new pivot point about a new axis, is equal to the moment of inertia about the center of mass plus mh squared, where m is the point mass, h distance away squared. So this is the parallel axis theorem. It's one of those things that needs a little bit of practice, and we'll get some practice in class, and we'll go through some demos or examples that we can kind of get our hands on and see if we can't conceptually figure out how this all works.